Hello everyone, I am Ahmet Selim Ayaz from the Physics Department at Bilkent University. Together with my partner Kaan Emre Emanetoğlu, we conducted a project for the PHYS211 course titled Investigation of a System of Two-Coupled LC Circuits. The main objective of this study was to examine the dynamics of a system possessing two degrees of freedom. Specifically, we analyzed two LC circuits coupled together by a shared capacitor. In physics, when you couple two oscillators, the system doesn't just vibrate randomly. It has specific patterns called normal modes. Using Kirchhoff's rules, we theoretically derived the equations of motion for our system. We predicted the existence of two distinct modes. The first one is a low-frequency mode, and the second one is a high-frequency mode. An interesting theoretical property of this specific coupled system is the relationship between these modes. The high-frequency mode is expected to be approximately the square root of 3 times the low mode frequency. We also accounted for the internal resistance of the inductors, which acts as a damping force, causing the energy to decay exponentially over time. Based on our component values, we calculated our theoretical frequencies to be exactly 720 Hz and 1255 Hz. Now let's move to the laboratory setup to see how we verified this.
First of all, the theoretical angular frequencies are given with these equations. Here you can see the diagram of two couples LC circuit which we used in our experiments.
Here you can see the actual circuit we built. The system consists of two inductors and three capacitor banks arranged in an LC ladder configuration. We used 114 microhenry inductors, and for the capacitors we had a challenge. High capacitance components are usually polar, so to solve this we connected pairs of polar capacitors in series back to back to create nonpolar equivalents of 420 microfarads. This allowed the circuit to oscillate without damaging the components due to polarity reversal.
Even if we neglected the resistance of the wires, there are small amounts of resistance, which cause the voltage drop to zero with an exponential decay. To solve this issue, we used Arduino board to constantly charge the capacitors with square waves. We wrote a custom control program that sends a 5-volt pulse every 1375 microseconds. This periodically charges the left capacitor to initiate the oscillations. We wrote a custom control program that sends a 5-volt pulse every 1375 microseconds. This periodically charges the left capacitor to initiate the oscillations.
If you look at the digital oscilloscope here, you can see the voltage response across the inductors. Notice that it isn't simple sine wave. It is a superposition of two normal modes we discussed earlier. We measured the actual oscillation frequencies from these traces. We found that the first mode at 720 Hz, which matched our theory near perfectly, and the second mode was measured at 1320 Hz, which is a very close match with only about a 5% deviation due to parasitic capacitance and the noise of the oscilloscope. We further confirmed these frequencies using an LT-SPICE simulation and fast Fourier transform analysis, which showed clear peaks at the predicted frequencies. In conclusion, our experiment successfully demonstrated the behavior of coupled oscillators and verified the theoretical normal modes. Thanks for listening.